Namaste. Good morning, guys. Hey, I'm gonna be doing a kind of a hodgepodge video right now that dealing with waves and various aspects of them. So just kind of bear with it, all right? Because I'm kind of throwing a few things together and just kind of scrunching it all in one video. All right. So the first thing I want to talk about is in terms of simple harmonic motion. One of the entities that falls into that category are waves. Why? Because waves repeat themselves. All right, as we live in the ocean state, so every Rhode Islander knows what waves are like, and they just they roll in from the bay and from the sound and so on, and it's obviously a repetitive type of motion. All right, so let's talk about waves for a second. All right, there are two different types of waves. And the first and most familiar is called a transverse wave. So that looks like this. Okay? And let's say that this would be like where the water is flat. Let's say I made it completely symmetric like that. A transverse wave is what you think of when you think of a wave. And what happens with a transverse wave is the energy goes in one direction, but the medium, and listen to the word I'm using, the medium is what a wave travels through. But the medium goes up and down like this, okay? So the energy travels at 90 degrees to the actual particles in the medium, okay? All right, so different parts to a wave here, to a transverse wave. If this is the flat line, or let's go to that word equilibrium point, then from the equilibrium point to the top right there, that's called the amplitude. Okay, and the high part of a wave is called the crest. Okay, the crest. And then the low part is called a trough. Okay, like what animals eat out of and so on. And the distance from crest to crest, now if the wave is symmetric, it'll be the same distance from trough to trough, but it's defined as the distance from crest to crest is called the wavelength, okay? All right, and wavelength is given because we're already using L for various other things like the length of a pendulum or something like that. We give it the Greek letter lowercase lambda, which kind of looks like a funny backwards K or something like that, okay? Now, the speed of a wave traveling through a given medium, all right, so V is related to the wavelength, all right, and it winds up being the wavelength times the frequency, right? And this will tell you how fast a wave is going or can go, or a wave of a given frequency can go in a given medium like air, all right, water, and so on, all right? Anyway, so there you have that, okay? The second type of wave is called a compression wave, okay? And a compression wave is, well, actually, examples of a transverse wave are water waves, like you know of. And also another example of a transverse wave is actually light itself. Light is we get into this in AP Physics 2, when we do optics, but light is actually a transverse wave, okay? What it is, it's an oscillating electric field, okay? And then at 90 degrees to that is a magnetic field, hence the term electromagnetic. But light is a wave. It has a frequency, it has a wavelength, and so on, all right? And actually, visible light, what you and I used to see with, is only a very, very, very small band of all of the types of, all of the frequencies of light that there are out there. But light is actually a transverse wave. Now, a different type of wave is called a compression wave, all right? And normally, if I were in class with you, I would demonstrate this with a slinky, and you put a slinky on the ground, and you kind of squeeze part of it back, and then you let it go, and the compression, when you squeeze it, we say it's compressed, and that compression shoots forward, okay? And that's a type of wave. And the way we draw it is like this. So let's pretend we're drawing a slinky, all right, and we're looking at it sideways, all right, and these are the rings on side, sideways of a slinky. And so in a certain part they're close together, and then they're stretched out as normal, and then close together again. All right, and this part right here is called a compression. Okay, and the compression would be traveling in a certain direction. So again, if you squeeze the slinky and then let it go, that squeezed part, the compression would actually travel along the length of the slinky. Okay, and let's say you did it in succession. All right, so you get a bunch of compressions like 1, 2, 3, 4, and you send them down the slinky like that. All right. This part right here, the opposite of a compression, is called the rarefaction. That's the stretched out part. Okay, and the wavelength for a compression wave is if you took the center of one compression and you went to the center of another compression, that would give you the wavelength of a compression wave. A good example of a compression wave is sound. Okay? And what winds up happening is when you speak, the vocal cords inside your throat, they do this, and what they do is when they go one way, the air in between them gets compressed, and then the air behind them, so as the vocal cord is moving this way, the air on one side is going to get compressed, and then on the other side it's actually going to get stretched out a little bit. And when your vocal cords vibrate and they do this, they are constantly making compressions in the air. And we as organisms have evolved to pick that up, and we hear that as sound. Okay, and so you can hear that in terms of sound. Obviously has a frequency. Sometimes the frequency of sound is called a pitch. I know I'm throwing kind of a lot at you here. And when it's vibrating fast, we hear that as high. And when it's vibrating low, we hear that as low. Or slowly. We hear that as low sound. So anyway, and that kind of brings us to a phenomena, okay, that we all know of. And let's for example, just kind of bear with me. Let's for example say this is a boat in the water and we're looking down on the boat. Okay, I know it looks like a bullet or whatever, but just pretend it's a boat on the water. And let's say that this boat is anchored, anchored in the water, so it's not going to move. But the pilot of the boat starts up the motors. All right, so the propellers are churning, and what do? Well, they make waves in the water. All right, and the waves would be completely circular around the boat, as you would expect, like ripples in a pond, and they would radiate out, as Grandma Golis would say, like so. All right, okay, but let's say now that the boat weighs anchor, and now it's able to go forward. So what's going to happen to these ripples? Because they're still being made by the churning of the propellers. Well, now the boat's moving forward, and we kind of all know this. All right, so here's the boat, and it's moving forward. And what winds up happening is the ripples get squished in the front, and they get stretched out behind it. So here's the direction of motion of the boat. Okay, so they're squished up here, and they're stretched out. Well, what does that mean? That means in front, the frequency of the wave that the motor is creating has actually been changed. A squished up frequency is a higher frequency, and a stretched out frequency is a lower frequency. Okay? So what happens is it seems as if just kind of by the fact that the boat's moving, that the frequency of the wave is changed, that it's making is changed depending on where you are in front of the boat, or by the boat, whether you're in front of it or whether you're behind it. So what does this have to do with anything? Well, this is an effect called the Doppler effect. Okay? And the Doppler effect is the apparent change in frequency of a wave by virtue of a moving wave source. Okay, so you have to have a relative motion between whatever is making the wave and yourself in order to detect a Doppler effect. All right. So what do I mean by that? Well, we've all had this experience, and we have it quite frequently. If a car is coming by you down the road, you kind of hear the motor, and you can tell if it's coming towards you because it sounds different. You also know if it's going away from you, because as it's coming toward you, you get like a higher sound, and then as it passes you, it goes a lower sound. So it's like high, low. That's a Doppler effect. Now, if you're inside the car, you don't notice a Doppler effect because you're moving with the engine. You're moving with the sound that's being created. But if you're outside the car, you definitely can hear a Doppler effect because what's happening is as the car is moving, the sound in front of it is getting squished up, okay, and its frequency is higher or its pitch is higher, and then behind it, it's getting stretched out. So if you're back here by the car and the car has gone by you, you hear a lower sound. Okay, and again, that's called the Doppler effect. All right. Now this happens with light, also. Okay, and if you remember when you were a kid and you learned the colors of the rainbow, Roy G. Biv. All right, red, orange, yellow, green, blue, indigo, violet. Okay, red is a longer wavelength of light, and purple or violet. And I did that really bad, is a shorter wavelength, okay? So, anyway, so it winds up, what does this happen? Now, I just also want to point out that this is actually a small portion of all the types of light or electromagnetic waves that there are out there, because you could vibrate, this is just what our eyes are tuned into seeing. You could vibrate lower than red and you would have infrared. It's the same thing as light. It's just light. It's just that your eyes can't pick it up. It's there. It's around you. All right. You could vibrate faster than violet, and you would get ultraviolet or UV. Okay. And then beyond that, you would have X-rays, and beyond that are something called a gamma ray. And then even lower, past infrared, you would get microwaves, which they vibrate even slower, and radio waves. Okay. So. Anyway, that's what's going on there. What does this have to do with anything? Well, in astronomy, astronomers notice the Doppler effect all the time, and we use it. Okay, and here's what I'm talking about. Let's say you have a star, and here's the Earth right here, and let's say the star is moving towards us like that. That star, if it's moving towards us, its light that it sends out would be like the boat. The light would be kind of squished up in front of it, making it a higher frequency or shifting it more towards the blue. Okay, so if it's coming towards us, we would say it's blue shifted. But let's say that the Earth was back here and the star was moving away from us. All right, its light, if it's moving away from us, would appear to be stretched out and would be shifted towards the red end. And we would say that the light is red shifted. Okay, so astronomers use this to determine, they look out into the universe and they look at everything that's out there, and we see whether it's red shifted or blue shifted, and by how much bluer or redder it appears, we actually tell how fast the star, or actually they tend to do this with whole galaxies, all right, are moving either towards us or away from us. And actually, this evidence or this technique that gave rise to the theory of the Big Bang, because when Edwin Hubble in the 1920s, 100 years ago, looked out into the universe and he started measuring red shifted or blue shifted, notice that everything in the universe is, every galaxy out there is red shifted. It's all moving away from us, okay? And so anyway, so it looks like that the universe is like in the aftermath of a large explosion, all right? And that's one of the ways that bits of evidence that he used to come up with his theory of the Big Bang, which is widely accepted today. Okay. The other way we use a Doppler effect in modern day life is with your GPS on your phone, because what you have is we have GPS satellites that are going around the Earth, okay? So here's the Earth, and we have satellites up there, okay? And they're basically sending out signals, okay, in all directions. And your phone picks it up. And by identifying what satellite it is, because they're all numbered and cataloged and all that, and what frequency it should be given out and what frequency the phone's actually receiving, we can tell whether they're moving towards us or away from us, or the phone can anyway. And if you do this with several satellites at a time, you can pinpoint or triangulate your position very accurately on the Earth, and that's how we get GPS. It actually uses Doppler. Another way to do this is with Doppler radar. Another use for this is, all right, so if you have a cloud, and let's say the cloud is moving like that in this direction, if you have a weather satellite, the weather satellite sends out a radar signal. If the cloud is moving, so it sends out a certain frequency, if the cloud's moving towards it, it's going to give that reflection a little boost and make it a shorter frequency on the way back, okay? Doppler shifting it, all right? If the cloud is doing the reverse and moving away, okay, then as the radar hits it, the reflection would be stretched out a little bit, and the satellite can tell that. And so we can tell whether the clouds are moving towards us, away from us. Obviously we have to compensate for angle, but we can do that. And you can, and that's how we use Doppler radar. Okay. All right. So there's that. Now the last thing I want to talk about, and again, I know I'm kind of squishing everything into one video here, is a concept called resonance. Okay. And resonance is the phenomena that every object, when struck, has a certain frequency that it wants to vibrate at, including you. Although, to tell you the truth, because we're mainly filled with water, when we get struck or our body gets struck, the energy is quickly dampened and the vibration is quickly dampened by all the water that's in our bodies. Okay, but let's say you're a more solid object like a piece of metal or a piece of glass. All right, and hold it. Yeah. No, it's not what you're thinking, so don't send this to Mrs. Maycomer. This is just, so this is a wine glass, and if you listen to it, all right, you can hear that when A is an A, I don't know, musician people would know this, but, all right, so when I do this, when I strike it, the glass vibrates, and it makes the air inside vibrate and makes sound, so it's making spherical compression waves as I do that, okay? And that note right there is the resonant frequency of the glass. Now, I'm going to do this demonstration, okay? We'll see how this works out, hopefully. All right, I'm going to take you guys over here, right to the desk, and turn on the light. All right, okay. So here we go. I think you can see the glass, so let me do that. All right. Now I'm going to do my favorite parlor trick, okay, where you take a little water, you put it on your finger, and let's see if I can get this to go. Come on now. It's going to ruin my whole video if I can't do this. Alright. There we go. Oh, I can feel it going. There we go. I'm amazing. Yes, I am. Yeah, you're right. I am. You have an amazing physics teacher. Okay, now what's going on is the glass is vibrating, and you're hearing it as I rub my finger over the top of it. The resonant frequency of this glass is probably about 300 some hertz. So it's vibrating probably between 300 and 400 times every second, like that. And so as my skin goes over the lip of the glass, it's actually skipping a little over 300 times a second, like that, and you're getting this resonant frequency. Okay, and that's the resonant frequency of the glass. Now, why is this important? Well, you future engineers really need to know this, because when we design buildings and bridges, All right, let's say you're designing a building, and that building will have its own resonant frequency. Well, if it's a factory building and you're going to have machinery inside, and that machinery is cycling at anywhere near the resonant frequency of the building, what'll happen is it'll start to shake the building. Okay, so what I'm doing with this glass is now if I kept doing this, and in time, I'd eventually break the glass, and you don't want to do that, because I'm adding energy to the glass in time with its resonant frequency. So if you had machines inside a building that you built, and the cycling of those machines was near or at the resonant frequency of the building, eventually you would shake the building apart if you did it enough and they ran enough. So you have to watch out for that. If you build a bridge, and where I'm going to send you the video of the Tacoma Narrows Bridge I want you to watch, all right, where what happened to the bridge in the 1940s when they built it was they built it over a gorge, and the wind went down, or the gorge, and it hit the bridge, and to the gorge and the wind, the bridge is just kind of like the reed of a saxophone, and it started to vibrate at the bridge's resonant frequency, and eventually the bridge shook itself apart. Okay, so that's why resonant frequency is kind of important. What are musical instruments? Musical instruments are just very simply devices that human beings have invented that can change resonant frequency very fast. So when you pluck the string of a guitar, it resonates at a certain frequency. When you put your finger on the string and pinch it up against the neck of the guitar, you just change the resonant frequency of that string. So when you pluck it again, it's going to have a different sound. All right, and so that's the deal with that. Okay, so I wanted to show you that and wanted to kind of cover that. And so, all right, make sure that you enjoy your apocalypse. I know I am.